Stars are normally considered to be immensely bright balls of nuclear fury, at least until they go into a post-normal star state, such as collapsing into a black hole or becoming a neutron star, or a cooling white dwarf. But in the early universe, things were a little different as far as star formation goes, and recent thinking has envisioned another type of star that's not at all like a normal main sequence star we see today. About 80 to 100 million years after the Big Bang, the universe's clouds of hydrogen and helium began to cool. This unusual situation may have allowed for a rather odd first generation of early stars that were dependent on dark matter to form at all. These extremely early stars would have been enormous. They had a lot of material to work with at the time, meaning they could have been 500 to 1,000 times more massive than the Sun, and physically much larger in diameter. If these stars indeed existed, they operated very differently from the normal fusion energy of stars as we know them. Known as dark stars, by nature they would be cool and ill-defined, and not radiate invisible light, hence the term dark. But they would do so at other wavelengths. Instead of nuclear fusion, they would instead have been powered by dark matter heating. This might have allowed for two types of early star: dark matter dependent stars, but also the first generation of normal stars producing heavier elements. Detecting these stars is a problem, however, even for the James Webb Space Telescope, which is designed to detect the earliest, most distant normal stars. The reason is dark stars should emit in gamma rays, neutrinos, and even antimatter, but not in the visual spectrum, making them very difficult to search for. They would probably congregate at the centers of early galaxies, due to those being the densest areas of dark matter concentration. It goes both ways, however, in that if dark matter can fuel types of stars, there should be other evidence of its effect in neutron stars and white dwarfs at the centers of galaxies. Yet this has not been seen. Yet again, this is a problem for the existence of dark matter, but without it, it's an equal problem, because our ideas of gravitation at long distances are flat wrong. And the evidence we do see of dark matter would still need to be accounted for with something else. What might be possible, however, is to use instruments like LIGO in gravitational waves to look into dark star mergers, which may well be the easiest method of detecting them. But there's an oddity here. In 2011, observations by the Hubble Space Telescope of one of the most distant galaxies ever detected showed an odd signature drop-off in infrared. The problem is that it's difficult to prove the observation with the capabilities of Hubble, so no one is sure just what the detection represents, other than a tantalizing hint that this odd class of star may actually exist, or have existed early on. If dark stars could be detected unambiguously, however, it would provide strong evidence for the existence of dark matter as a whole, a major question in cosmology. The James Webb Telescope offers an advantage because dark stars should radiate at longer infrared wavelengths that it can detect that might better show the signature of a supermassive dark star. There is strong hope here because Webb has already detected similar signatures from very young stars within stellar nurseries that were not detectable before with any other telescope. But even if you could prove the existence of dark matter above and beyond its overall effect on galaxies and dark stars, it still doesn't tell us what it is, and that may be a key in answering a new mystery that's cropped up recently. It's an issue with antimatter. The question of antimatter has always been murky. We know it can exist because we can create it under lab conditions. It doesn't last long. Antimatter famously annihilates with normal matter if they come into contact. But we live in a large universe full of mostly empty space, where particles of antimatter can go a long while without running into any normal matter. This raised a question. If that's the case, then where's all the antimatter that should have been produced in about equal amounts to normal matter during the Big Bang? Originally, the answer was that it might still be around, and you could never tell the difference between a star made of normal matter and an anti-star, because both forms of matter behave much the same otherwise. They shine the same and operate the same. In the intervening years, however, ways to possibly detect the presence of large amounts of antimatter in the universe have been devised, but no one really expected to see it, defaulting on the appearance that the universe presents of there being no large amounts of antimatter out there. other than in rare positron fountains, a mystery in their own right. At least that was until an experiment unexpectedly and out of nowhere showed large amounts of it. In 2018, an experiment mounted on the exterior of the International Space Station, known as the Alpha Magnetic Spectrometer, detected something unusual. The scientists involved found what appeared to be 2 anti-helium nuclei, in addition to 6 more of another isotope previously. If that detection was real, which is still an open question, it's based on one instrument, then it's far too much antimatter for us to easily run across with an experiment like this, and it's in a form far too complex than it should be. That said, the numbers aren't huge. The detector sees many millions of times more regular helium nuclei than it does anti-helium. But the effect is still there in that they shouldn't see any anti-helium at all. There are several ways that these particles could be created, but one possibility is that they are being created in antistars, lurking out in the universe somewhere. And evidence for that seems to be mounting. Another group of researchers linked the anti-helium finding to yet another mystery: strange gamma-ray sources discovered by the Fermi Large Area Telescope that also remain unexplained. Antistars would normally look just like regular stars, emitting photons at the identical wavelengths as their normal matter counterparts. But space isn't completely empty, so you should have particles and gas falling into the antistars and annihilating, which should produce bursts of gamma rays, but at very specific wavelengths. That was seen. But other astronomical sources of known origin can also do this, so any known sources like that were eliminated from the study, leaving 14 candidates for antistars. The team notes that they probably aren't antistars, and other more mundane means should be considered first. But if the observations continue to line up with that of experiments detecting anti-helium, the prospects of antistars will have to be carefully examined. One problem is that there are 14 candidates, which is a lot, and it would suggest that antistars are relatively common, which seems a bit hard to swallow. They should be rare. But then there's the anti-helium detections. We know antiparticles can be created in 2 known natural ways, one more hypothetical than the other. One is through cosmic rays, and the other through the interactions of dark matter. The problem is, the odds for either one of these options being the culprit seem really thin, which then points in the direction of antistars being more plausible. This is because of how hard it is to form a large antiparticle. Forming an antiproton is straightforward. It's something that can be done in the lab. It gets harder though when you start to mess with things like antideuterium. It's more complex. Anti-helium is even worse, to the point that the heavier the atomic nucleus, the more difficult it gets for it to form outside of an antistar. So in nature, the possible avenues to create these antiparticles works like this. The first is from high-energy cosmic rays emitted by supernovae. This process is called spallation. So a high-energy particle comes cooking along through the interstellar medium until it hits some gas or something, and in that energetic collision, an antiparticle can result. The problem with the anti-helium detections is that 6 were anti-helium-3 and 2 anti-helium-4. That level of complexity is almost statistically impossible to happen enough through spallation for it to be readily detectable. This stuff was seen the earliest moment we could detect it. If it even happens much at all in the universe, it's not impossible, but it's a step too far for nature except under very rare conditions so far as we know. The other is the elusive dark matter. This one is more ambiguous, and honestly almost on level with the idea of an antistar kicking out particles. It's that some ideas about dark matter are that particles of it, if it is indeed a particle, might annihilate with one another under certain conditions, and that might too create antiparticles. Other than the issue of potentially not existing, this process would also have a huge problem producing enough antihelium, especially anti-helium-4, in enough of a number for us to be able to simply turn on a detector and see it right off the bat. So the antistar option sits on the table as the best fit. The Achilles heel, however, here may be in errors in the detection. That hasn't been eliminated yet, and the analysis is ongoing, along with further experiments to try to verify the anti-helium detections. In other words, it all could have been a fluke of the detector, and if it's never verified, then the idea of antistars goes back to the purely hypothetical. But say for a moment it turns out that anti-stars do exist. They would require at least a modification of just how we think the evolution of the early universe occurred, which is starting to happen anyway due to somewhat rather odd results from the James Webb Space Telescope that are for another video. But if you play with the idea of anti-stars and assume they exist, they would be true relics dating from the earliest times of the universe, a phenomena that are no longer currently forming. The clouds they formed out of would have likely long ago annihilated on contact with normal matter, and another mystery would await. Exactly how did the anti-stars manage to survive so long? That would be a difficult question as well, since they probably should not have in large numbers, assuming we are not in some special circumstance, like a jet of them pointed in our direction, or one located unusually close by, or they're created by some other process we aren't aware of yet. But another question would be, what are the rules for anti-stars? If they behave like normal stars, do they follow the same classifications of mass and temperature that normal stars do? The answer seems a likely yes. So was it ever possible to form massive anti-stars that went supernova and sprayed antimatter into the early universe in huge fits of annihilation? Is there any evidence left of that? Would it have been a cataclysm far greater than an already cataclysmic normal supernova? The questions are many, but antimatter is a mysterious substance. Not in itself, it's just an anti-counterpart to normal matter that we know exists and can create, but rather in how nature generates it, both in the Big Bang, but also now. And there's still the matter of the antimatter positron fountains found in the Milky Way, that probably exist in a large number of galaxies in the universe. We still haven't the slightest idea of what's causing these gigantic streams of 15 billion tons of positrons per second, only that we see them annihilating. You can play around with ideas of neutron stars or supermassive black holes creating the circumstances of that, but why don't they more commonly do that? You could also question anti-stars here, though it's hard to see how one would survive in the densest parts of the galaxy. But the reality is that with antimatter, it seems the mysteries of how it comes to be in the universe have only just begun. Thanks for listening. I'm futurist and science fiction author John Michael Godier, currently introducing a new term to the channel lexicon, garden hubris. Oh yes, it's spring here, and as a longtime gardening and plant enthusiast, currently having gone overboard with urban square foot gardening and putting containers everywhere, the amount of growth is particularly good this year with all manner of lettuce and spinach harvesting going on. But perhaps it's too strong, and the plants seem to have struck a Machiavellian deal with the rabbits and squirrels this year, as nothing is getting eaten. It's quiet. Too quiet. Keep a watchful eye on the greenery, and be sure to do the same with my books at your favorite online book retailer, and subscribe to my channels for regular in-depth explorations into the interesting, weird, and unknown aspects of this amazing universe in which we live.